we're going to continue talking about our circles and continue on the circle unit that we've been talking about. We talked about our circle angles last week in the constructions. This week we're going to talk about chords and tangent lines. So we have two types of lines that occur in circles or outside of circles called chords and tangent lines that are special. And we're going to talk about what is unique when you get a chord and a tangent line, what happens when you get those together, and what they form, and what are some special properties. That's going to be the main thing today, and tomorrow. Today we're going to mainly focus on angles, so we'll still focus, we have technically two other types of angles that occur within circles that we've talked about from last week. And so we're going to talk about those two special types of angles today, and then tomorrow we'll talk about some special properties that chords have and that tangent lines have. Other than that, those are the only two things we're going to learn, so today, tomorrow, and then Thursday practice, Friday assessment, like typical. Any questions on that or the order this week?
So is this pretty easy since we're not like, time on it?
I think so. The angles are going to be very similar to angles we learned last week, and so assuming you still have the skills from last week, assuming you still remember those things that we talked about last week, I think you should be able to practice pretty easy, especially today. Tomorrow the theorems are a little bit different because it's more of just properties that they have. So like if this intersects this one, you multiply these two together and set that equation. So it's just some things to memorize, but other than that, I don't think it's too difficult. And so I think we'll be okay. So we have this tangent line to start with. What do you notice about this tangent line? So we have two examples of tangent lines and one non-example of a tangent line. What do you notice about these that make something a tangent line or not? Alex?
They're outside the circle.
So our tangent lines are outside the circle. What else? It only touches the circle at one point. Were you going to say something, Gabe? It doesn't go through the circle. So a tangent line is basically all those things combined. It's not passing through the circle. It's going outside the circle, and it's only going to touch the circle at one exact spot. It's basically like it goes and it glances off the circle and then just keeps going. So it only touches at one point and then keeps going. And that's really what they're. And because of how they touch the circle at one spot, we get some special types of properties that are formed from this that we'll talk about today and tomorrow specifically. One way to remember a tangent line is you can think about when someone's telling a story, they're sort of talking about something and they're telling a story and then they start talking about something else and they sort of like go on a little rabbit trail. That's also called going off on a tangent. It's like we go off in a different direction. So that might help you remember what a tangent line is because you're like with a circle and then you go off in a different direction, but that might help. But those are tangent lines. They are technically related to like our sine, cosine, tangent that we learned earlier in the year because it's still that same word, but you won't really learn about that connection until trigonometry or pre-calculus. So don't worry about that. But the tangent line technically is connected to sine, cosine, tangent. That's where we get the name, but that's not important to you. So that's our tangent line. The other type of line we're going to talk about within circles is called a chord. So we have two examples of a chord and one non-example. So what do you notice about chords?
It touches the circle like
it touches the sides.
So both ends of your line segment are going to be on the ends, or are going to be on the outside of the circle. It's going to be on the edges of the circle. It passes through the inside of the circle. What else do you notice?
How do you have to solve through on the other side of that circle?
We're going to talk about some angles and arcs today. Not necessarily. We'll have more information for stuff like this. It's not going to be like you're just given this line and you have to find some pieces. We'll talk about some examples and we'll look at it. Yeah, it will give you more information. Why is that non-chord? Why do you think that's not a chord? It doesn't touch the other side. If I had a chord that passed through, has an edge on each side of the circle, but went through the center, is it still a chord?
Yes.
What do we call it?
What?
Would it be a chord?
It's already a chord. It's a diameter.
So if you had a chord that went all the way through and went through the center, it would be a diameter. So diameter technically is like a special type of chord. It is a chord, but it's one step ahead because it passes directly through that center. Chords in general don't pass through the center. So if it passes through the center, it's a new step. It's a diameter, which is special. Chords are just their own little thing that just pass across the circle. And so when we get chords, we often have these chords intersect. When these chords intersect, we get some angles. So we have two types of angles. We have two diameters intersecting here, and then we have two chords intersecting. What are some things that are similar that you notice about these? We have some vertical angles, okay. What do we remember about vertical angles? Non-supplementary. They're always going to be congruent to each other. So vertical angles will always be equal, they'll always be congruent, and remember, you get vertical angles anytime you have an intersection, and they're always opposite of each other. So these are vertical angles, these are vertical angles, these are vertical angles. What is different about the two? One has a central angle, or one is like on the center, so it's all central angles. The other one's not. It's not central angles. So with this, assuming we figured out what these angles were, we could figure out what the arcs are. But if we knew what this angle was, it doesn't necessarily mean it's going to relate to that arc, because it's not on that center. It's not a central angle. And so with chords, we're going to have to use a different way of relating those angle measures of the chord to the arc measures that are formed with it. A nice thing to know, though, is because these are vertical angles, assuming you find one of those angles, you know what the other one is. Because they're always going to be equal. So if you find this is 50 degrees, you know the other one's also 50 degrees. Are we okay with this? So this is where your notes actually start, where you're going to pick out. So we have three examples of some chords intersecting, some angles formed by chords. What do you notice about the combined measures of the arcs and the chord, or the angles of these situations? What do you pick up?
It's that the angle is like the distance. I don't know. So the angle of like not the arc.
Like the
This
inside angle?
sounds so stupid. Okay.
Like this angle?
Yeah.
Okay, so your actual angle.
It's like a number in between the two arcs.
Okay, so your angle is in between your two arcs.
I don't
Okay.
know.
No, that works. Yep, that's true. That works for all of our examples.
Or the distance. They're all multiples of, I don't know, I want to say 4, but like that's not. I feel like like
Not
50
necessarily,
to
because
30.
75 is in a multiple 4.
I don't know if it's like a coincidence for two of them, but like 50 and 30, or no. No. Like the midpoint between 50 and 175, the midpoint between 30 and 50 is 40.
Okay.
I don't know.
Midpoint. How do we find the midpoint? Taking way back one. What did we do for that?
Add up the x's and cut them in half.
So you added them together and divided by 2, right? So we took 50 plus 30 and divided by 2. 50 plus 30 is 80, divided by 2 equals 40. 80 plus 20 is 100, divided by 2 equals 50. And then 100 plus 50 divided by 2, 100 plus 50 is 150, divided by 2 is 75. Very good. So yeah, in a sense, it is the midpoint, or the mid number between the two. So take those two arcs, add them together, divide by 2, find the mean of the two arcs, if you will. And that is always your angle. Once again, as soon as you figure out what one of these angles are, you automatically know what that other one is, because they're vertical. They'll always be the same. And so if you know this one's 50, you know that one's 50. And it doesn't matter which one you solve for, you typically just need to solve for one. Are we okay with this? So it's similar to our outside angles we talked about last week, but the outside angles were you took the larger one minus the smaller one divided by 2. With this, it doesn't matter which one you add first, because with addition, it doesn't matter which order you add. 2 plus 3 is still the same as 3 plus 2. It doesn't matter what order you just don't add them together. Are we okay with this? Good? So these are our chord angles, or intersecting chords, or you can call them other angles or inside angles. I don't know, whatever name you want to call them. We don't really have a typical. But if we were to solve these, we can just use that same pattern, the same method. You take your arcs, add them together, divide by 2. So 160 plus 130, that gives you 290, divided by 2, gives you 145. And that would be your angle. See if you can get the second one. Add the 2 arcs together, divide by 2. Take your 2 arcs, add them together, divide by 2. So we had 135 plus 75. Add those together. We got 210 divided by 2. What did our solution turn out to be? 105. Very good. My goodness. All right. What do you notice about that last one?
Because it has the angle measurement, it just doesn't have the arc.
We have an angle, but we don't have the arc. We're missing that x. What else? Do you notice anything else?
Those are the arcs of the angle.
So our angle always needs to be the one that's intercepting that arc. But if we look, 1 of 2 is to the right. Our angle should either be this top one or this bottom one. It shouldn't be over here to the right or to the left. We need to be one of these 2. What can we do?
You can
Minus the other arcs.
It'd be like
So
one
one
of
of
two. Because it's that if you went like that, isn't that like 360?
So we know a full circle is 360.
So 1 or 2 on the vertical to make it the same thing. Add those together and then just divide by 2.
Okay, so we know these together are 1 of 2. And so,
the 2 and 4, the 360 minus 2 and 4. And
When the divide by 2 would be that, and then you can solve.
okay, that works. That's completely feasible. A little bit easier of a method that we can think about is this is a line. That means together, these 2 angles in here are going to be subtracted. They're going to add to equal 180. So rather than having to figure out the 102 and the 102, add them together, divide by from 360, you're really doing the same thing except you're cutting your work in half. All we need to do is do 180 minus 102, and that gives us 70. And that might be a little bit easier of a step rather than having to do the way you were doing it was perfectly fine, and that would perfectly work. This might just be 1 or 2 steps less. So mathematicians are lazy, so we try to find the easiest way to do something. Okay, good. Now that we have this angle, can we solve?
Yeah.
How would we do that?
95 plus x divided by 2 equals 70.
So our 2 arcs added together, 95 plus x divided by 2, equals our angle of 70. Very good. What would you do first to solve this?
Multiply 2.
Okay, so we want to get rid of that denominator, so we'll multiply this. So we'll have to do 78 times 2, which should be 156, equals 95 plus x. Last step, subtract 95. Good. Invert that constant, and we get x equaling 95, or 156, 61. Very good. So 61 is your solution. Awesome, for x. So as long as you know 2 pieces, as long as you know either the angle in an arc or both the arcs, you should be able to solve for any of those missing pieces. You should be able to find what you're missing on those chord angles. Are we okay with this? Any questions on this one? And remembering that those chords are supplementary to each other, to be able to find those other missing angles is also very important. So if we look further at these other two, this first problem says, why is the measure of CDE incorrect? So what's different about CDE? Why is that wrong?
Because it's not, the arc is not the same as the angle.
So we know central angles, when your vertex is on the center, the angle and the arc are the same. But because our vertex isn't on the center, it can't be a central angle. So it's not going to be 40. We know that's not true. How would we find what the angle is?
80 plus 40.
80 plus 40 divided by 2. That gives us 120 divided by 2 equals 60 degrees. So 60 is your actual degrees, not 40. Once again, it's because it's not a central angle. It's made of two chords that don't pass through that center. Very good. All right, one other challenging question. We have 30 degrees as one arc, 3x plus 30 as your other arc, and then 5x plus 50 as your angle. How can we set this up to solve?
X plus 50 in front of the 3x plus 30 is equal to 30.
Not quite. I think you're on the right track, but we need to remember that it's both your arcs added together divided by 2 equal your angle. So rather than doing these two pieces added together, we're going to do combine. We're going to do 30 plus 3x plus 30 divided by 2 equals x plus 50. We're just going to switch it around because we want to remember that it's the two arcs that add together. So very good. What would you do first? There's a couple of steps you could take. There's a couple ways you can go about this. There's not one correct way. What would you do? Combine like terms. What like terms are you talking about?
Like 30 and 30.
30 and 30. Okay, so we can combine that. That will give us 3x plus 60 in your numerator over 2 equals x plus 50.
Now you have to get x on one side, so subtract x to 3x.
What if I just multiply by 2 first and then because
So because this one's in a fraction and this one isn't, we can't really combine them by addition or subtraction until we get rid of that denominator. So we're going to have to actually get rid of the 2 first before we can combine any other like terms. So we'll multiply by 2. The thing is, if I multiply 2, I have to multiply that whole other side. So not just the x, or not just the 50, I have to multiply both of them by 2. And you can think of this kind of like a distribute. We're distributing that 2 into each piece of that right side. So, congratulations. You just set on my desk. Thank you. That's not throw, please. So we have 3x plus 60. 2 times x is 2x. 2 times 50 is 100. We have 2x plus 100. And now, Morgan, what would you do?
Subtract 2x to 3x.
Now we can get those x's together. Combine them. So subtract 2x. So we have 3 minus 2x is just a single x. Plus 60 equals 100. And then last step, we just need to get that x by itself. So inverse or constant. Subtract 60. And we get x or 1x equals 40. Very good. So once again, assuming we have those values, assuming we have those pieces of information, all you have to do is just plug them into that formula, plug them into that pattern that we recognize, and you should be able to solve. Any questions over this? Concerns? Honestly, I think this is easier than what we were doing last week. Because last week you had to do the subtraction, you had to worry about subtracting and multiplying the negative in there. With this, you don't have to worry about it. It doesn't matter which order comes first, because it's just an addition. So honestly, I think this is much easier than actually the outside angles you were doing last week. All right, so we have one other type of angle we're going to talk about today. So this is an angle that's formed by the intersection of a chord and a tangent line. So we have the tangent line on the bottom and the chord just inside this circle. What do you notice about these arcs and these angles? So our chords are, it doesn't necessarily always have to be at an angle, but most of the time, yes, we'll have them.
The arc is
The angle.
Yeah.
Or the tangent line touch.
Yeah, your chord and your tangent line will touch, and that will give you your little vertex of your angle right there on the edge of your circle.
Your angle is double of your arc, so like 130 plus 130 equals 260.
Yeah, flip it around. Your angle is half the arc. The arc is half the angle.
What did I say?
I think you said the angle was double the arc. Yeah, just the other way around. Yeah, you're right. So 260 divided by 2 is 130. 100 divided by 1 or 2 is 150 or 50. So on and so forth for the rest. So your arc is always half of your angle. Or sorry, the other way around. Your angle is always half your arc. Do you notice anything else? I saw someone say that. Or heard someone say that. That's all. I can't see speech. What do you notice about these two angles?
Yeah.
So your angles are always going to be supplementary because they're both on that tangent line. They both form a line. Your two angles will always add together to equal 180. What else do you notice? There's one other thing. What do you notice about the arc measures? Your two arcs together equal 360. The two arcs will always equal the full circle because you only have 2 points of intersection on that circle. So together, both of these will always equal 360, and your two angles will always equal 180.
Is there like a fancy word for that, like similar to supplementary?
Added together to equal 360? Not that I'm aware of. There might be, and I just don't know it. Supplementary and complementary are like the two that we talked about. Complementary is your 90, supplementary is your 180. But I don't think, there probably is one for 360, but it's not in my brain at the moment, so I don't know actually. Good question. So because of these three special things, and these three special patterns we found, as long as you know one piece of information, you can find every other piece of information about the circle. Assuming we just know one of those angles or one of those arcs, we should be able to find the rest. And so the reason these work, the reason it's half, if we think back to last week we had our inscribed angle, the arc was half. And if you think about this tangent and intersected chord, it's the same thing as an inscribed angle. But rather than having that angle or that other line on the inside, we just took that other chord and we pulled it outside the circle. So it's still an inscribed circle, or still an inscribed angle. We just pulled it from being a chord to outside into being a tangent. And it still works the same way. It's still going to be half the intersected arc. You just now made two angles in a sense. But it still works the same way. And so as long as we know one piece of information, we should be able to solve for all of the rest. So for that first one, we have that angle, we have the angle of 117. We want to try to find what both of those arcs are. How can we find that? Would 53 be the other what? So we know they're supplementary, so that means the other one would be at 63. So 180 minus 117 gave us our other angle of 63. Good. So we have both those angles. How can we find the arcs? Multiply by 2. So 117 times 2, that gives you 234. And that's your other arc measure, that's your first arc measure. How would you find the other one?
360 minus 2.
Either of those work. You can take 63 times 2, and that'll give you your angle, or you can take 360 minus 234, and that also gives your angle. Once again, there's multiple ways you can solve this. And so that, we know the other one, through whatever method you choose, should be 126. So once again, thinking about a whole 360, or thinking about how the angle is half of the arc, either way you can use to solve. All right, so what about solving for x on that second one? What would you try?
130 divided by 2 is 65. Is that your
130 divided by 2 gives you, was it 65?
And
That gives you this angle in here.
180 minus 65.
And knowing that this is supplementary, knowing that it's a linear pair, we can do 180 minus 65, and that is 150. Very good. Once again, another way you could have done it is you could have thought, this angle up here is 360 minus 130, which is 230. Divide that by 2, that's also 115. So Once again, there's multiple ways to solve this. What about that last one?
Yeah.
Yeah, no?
I just don't know how you would set it up, but just say like,
Yeah, put it over and over.
So what's our rule? What is our rule about angles and arcs with this one?
The arcs are twice the
So the arcs are twice the angle, or that the arc is half, or the angle is half the arc.
so would it be 14x plus 10 divided by 2 equals 8x minus 5?
So your arc divided by 2 equals your angle. That's how I would set it up. You could technically do 2 times your angle equals your arc. That's another way of going about it. But essentially it's the same thing. Now what would you have to do first though?
Get rid of
Get rid of that denominator, so we're going to multiply by 2. But once again, you're multiplying that entire other side by 2. It's not just the 8x, it's not just the negative 5, we have to multiply everything by 2. So it's like you're distributing it in each of those pieces. We have 14x plus 10 left over on the left side. And then 2x times 8 is 16x. Negative 5 times 2 is negative 10. And now from here we can start combining our length terms and solving. We get our x's together, so I would say subtract 14x. And once again, you might do it in a different order, that's okay. That gives us 10 equals 2x minus 10. Add your constant over a 10. And that gives us 20 equals 2x. And then divide by 2 to get x. Now, but once you set up that problem, it should be pretty easy to go from there. You just have to remember to distribute the 2 in the whole thing, otherwise you only get part of the answer.
Are we done today?
Yeah, I practiced pretty good.
Okay, can I go back?
Any questions about any of this? Once again, tomorrow we're going to continue talking about chords and special things that are formed by chords and tangent lines. Other than that, I'm good.